All right, we're going to work through the proof for the DeMoivre's theorem. We're going to do this proof by induction. What we're going to show is that z to the n equals r to the n times the cosine of n theta plus I sine n theta. The work is here for you. I will just explain certain parts of it. The first part says we need to show that it's true for n equals 1. That's part of the proof for induction. So we plug 1 in, and when we do that, we get that r cosine theta plus I sine theta is z to the first power. But that's the definition of a complex number, so the theorem does hold for n equals 1. The second step of an induction process says to assume that it's true for n equals k. So that's what we do here. We just say, therefore, z to the k equals r to the k times the cosine of k theta plus I sine of k theta. And the theorem holds for n equals k. The last part of the proof by induction is to prove for k plus 1 items. So we start with z to the k plus 1, but we can't use the theorem, so z to the k plus 1 can be written as z to the k times z to the first. So we make our substitutions for z to the k and z to the first. Now, because we're multiplying, we can rearrange and we can pull the two r's together. So we have r to the k times r. And then we have the cosine k theta, I sine k theta, times cosine of theta plus I sine theta. Well, r to the k times r ends up being r to the k plus 1 because you add the exponents. And then I FOILed out this bottom piece. So cosine k theta times cosine of theta, cosine k theta times I sine theta, I sine k theta times cosine of theta, and I sine k theta times I sine of theta. When I take the I times the I get that's where the I squared comes from for that term. Then I just rearrange because I'm just adding along in here, and so I just reorganized because I want these two terms together for my sum or difference formulas. R to the k plus 1 doesn't change. And then I want these two terms together because they both have an I in them. Now we know that I squared is negative 1, so instead of plus I squared, it becomes minus. And so we have cosine k theta, cosine of theta, minus sine k theta, sine theta. And then I factored an I out here, and so we have I times cosine k theta, sine theta, plus sine k theta, cosine theta. This part right here is the sum formula for a cosine angle. It's the sum of cosine of k theta plus theta if you look at your sum and difference angle, sum and difference of two angles formula sheet. This right here is the sine of k theta plus theta, and that's what we have here with the I in front. But we can rewrite k theta plus theta as theta times k plus 1. And we can rearrange, since it's multiplication, we can say that's k plus 1 times theta. So then when we make that substitution back in, we say we have r to the k plus 1 equals cosine times k plus 1 theta plus I sine k plus 1 theta, which is what the theorem said it should be. Since it holds for n equals 1, n equals k, and n equals k plus 1 cases, DeMoivre's theorem holds for all cases.